Hey there, universe nerds. Today we're heading to the edge of everything, where gravity crushes matter, space-time bends into infinity, and yet somehow the laws of thermodynamics still apply. That's right. Even black holes, the most chaotic objects in the cosmos, obey the same rules that govern your coffee cooling on a desk. It's one of the most profound discoveries in modern physics, black hole thermodynamics, the bridge between heat, energy, entropy, and the cosmic abyss itself. At first, the idea sounded absurd. How could a black hole, which lets nothing escape, have temperature or entropy at all? In the early 1970s, physicists Jacob Bekenstein and Stephen Hawking were exploring what happens when matter falls into a black hole. Bekenstein realized something strange. If you throw something with entropy into a black hole, the total entropy of the universe seems to decrease. That breaks the second law of thermodynamics, which says entropy must always increase. To fix this, Bekenstein made a bold proposal. Black holes themselves must have entropy, a kind of hidden disorder stored on their surface, the event horizon. It was a revolutionary idea. A black hole isn't just an object, it's a thermodynamic system. The amount of entropy it holds is proportional to the area of its event horizon, not its volume. That means the information inside a black hole, the number of possible microscopic configurations of matter and energy, scales with its surface, not what's inside. It's as if the entire interior of a black hole is somehow encoded on its boundary. This insight became the foundation of something even bigger, the holographic principle, which suggests the whole universe might be described by information stored on a surface in higher dimensions. Then came Hawking's famous contribution. Using quantum field theory near a black hole's event horizon, he discovered that black holes emit faint radiation, Hawking radiation, meaning they have a temperature. That was the missing piece. Suddenly, all four laws of thermodynamics could be written for black holes, just like for any physical system. The result was a stunning revelation. Black holes weren't just cosmic traps, they were thermodynamic objects governed by elegant, universal laws. Here's how those laws work. 1. The first law, energy conservation. When a black hole gains mass, spins faster, or becomes charged, its energy changes in a way that mirrors heat and work in classical thermodynamics. 2. The second law, entropy never decreases. The total area of all event horizons in the universe can never shrink, echoing the cosmic version of heat never flows from cold to hot. 3. The third law, absolute zero is unreachable. You can't reduce a black hole's surface gravity to zero through any finite process. 4. The zeroth law, surface gravity is constant across the event horizon, like uniform temperature in thermal equilibrium. These aren't metaphors, they're mathematically identical to the thermodynamic laws we use on Earth. Somehow, the same physics that governs your cup of tea cooling also governs the most extreme gravitational objects in the universe. That unity is what makes black hole thermodynamics so mesmerizing. It connects the everyday with the infinite. The most mind-blowing part is the entropy-area relationship. For every square meter of a black hole surface, there's about 10 to the 69 bits of information encoded. That's an unimaginable density of data, enough that a black hole the size of Earth could store all the information in the visible universe many times over. This led to one of the biggest insights in modern theoretical physics, the information paradox. If black holes evaporate through Hawking radiation, what happens to all that encoded information? Does it vanish, violating quantum mechanics? Or does it somehow leak out, encrypted in the radiation itself? This question still drives some of the deepest research in physics today. As strange as it sounds, black hole thermodynamics might be showing us how gravity, quantum mechanics, and information theory fit together. In fact, many physicists think it could be the key to quantum gravity, the holy grail uniting Einstein's relativity with quantum physics. The way black holes store and process information might be the prototype for how the entire universe does it. In that sense, studying a black hole is like studying the operating system of reality itself. There's something poetic in how all this fits together. A black hole, an object defined by destruction, turns out to be one of the most orderly systems in existence. It follows strict rules, carries precise information, and obeys cosmic bookkeeping laws that never fail. Even at the edge of chaos, the universe insists on balance. Hawking once called it the ultimate triumph of reason, order at the brink of the abyss. So what is black hole thermodynamics? It's the realization that even the darkest places in the universe followed the same elegant rules as everything else. That entropy still counts, energy still flows, and information still matters, even when trapped by gravity. It's a reminder that physics at its core is universal. From the smallest atom to the largest black hole, the same laws whisper through the void. And that whisper, as it turns out, is warm.